Hello, everyone. Welcome to Pre-Lecture 17. Hope you have had a good break. This lecture is going to be all about buffers. So what is a buffer? A buffer is a solution that contains an appreciable amount of a weak conjugate acid-base pair. And so that is one of the keys that we'll talk about here in a second, is that you need a weak acid and a weak base in order to make a buffer. The buffer itself is a solution that's going to resist a change in pH when small amounts of a strong acid or strong base are added. Okay, and so an example that we're going to go through today that would be kind of the classic example of a buffer would be acetic acid. So that's this HC2H3O2 and sodium acetate, its conjugate base. When we have a mixture of those two, we would get a acetic acid acetate buffer, right? And so if we buffered a solution, and then in this example here, we have the addition of a small amount of, 1 milliliter of 0.01 molar HCl solution. In our buffered solution, we don't really see any change in pH as shown by our indicator here. Whereas if we don't buffer our solution, even 1 milliliter of a fairly dilute strong acid solution can create an acidic solution. Okay. Another way we could maybe visualize this is that, say we start with an equal amount of acetic acid and acetate shown here. If we were to add something like hydroxide, that would react with our acid portion of our buffer. So the hydroxide reacts with the acetic acid. So our amount of acetic acid would go down, but then our amount of acetate would go up. So any acetic acid that reacts with the hydroxide will form our acetate. Then the inverse, of course, would be true if we were to add some sort of hydronium source. That H3O plus would react with the acetate portion of our buffer. That acetate portion would go down, and the concentration of acetic acid would go up. And of course, this will all remain in equilibrium. Okay. So how do we then determine the pH of these buffered solutions? One way that we could do it is using an ice chart. So I'll go through an example here. So what is the pH of a buffer that contains 0.050 molar propionic acid, our HC3H5O2, a 0.045 molar solution of sodium propanoate, its conjugate base. And so if we were to do this, start it like we would start any other equilibrium problem by writing our chemical equation and our K expression. And so we could say C3H5O2 plus water is going to be in equilibrium with H3O plus, and our conjugate base C3H5O2, right? And so, and that will have a minus charge on it. And so this C3H5O2 is going to be represented by our sodium propanoate concentration. And so if we build our ice chart, and actually before I fill that in, let's write our Ka expression. Ka is equal to, as always, products over reactants, so H3O plus times C3H5O2 minus, sorry, running out of room there, over our weak acid H3H5O2, right? So we build our ice chart then. We would say that our initial concentration of our weak acid is 0.0500 molar propionic acid. Water is pure liquid, of course, so we don't count that. We'd say we have an initial concentration of 0 for a concentration of hydronium. Then the big difference here is we have an initial concentration of our conjugate base. And so we would say we have an initial concentration of 0.0450 molar propionic. Then, because we have a 1-to-1 ratio, we could find Q, but we know that K is very small, and so that we know that our change is we're going to lose some of our reactant and we're going to gain some of our product. And then if we combine our terms, we have 0.0500 minus x, right? Minus there. And then we have x, and we have 0.0450 plus x. Okay. Then same thing that we did before. We take what's in our equilibrium row and we plug it into our Ka expression, as well as plugging in our Ka value. And so when we do that, I got values of 1.3 times 10 to the negative 5 is equal to x times 0.0450 plus x. And then we also have on the bottom 0.0500 minus x, right? So we've introduced another variable here, but the good news is that we can still use our x is small approximation. So we can actually use it here and here. So anytime we have a plus or a minus x, we can still use our x is small approximation. And so that means that if we just multiply each side by 0.05 and divide each side by 0.045, we should be able to solve for x. So when we do that, I got x is equal to 1.44 times 10 to the negative fifth. And that is going to be equal to, if we look back at our ice chart, our concentration of H3O plus, right? And so if I were to then take the negative log of that, we would get the pH. So taking the negative log of that 1.44 times 10 to the negative fifth, get a pH of 4.84. Okay, and so that would be the pH. Okay, hopefully that made sense. And that would be one way that we could find the pH for a buffer system. So I'm going to clear that, and we'll go ahead and keep going on. The good news is the rest of this pre-lecture is talking about an actual easier way yet to find the pH. And so as long as our x is small approximation works, then we don't actually need to use an ice chart. Instead, we can use one equation that we used in lab the week before break, the Henderson-Hasselbalch equation shown here, where pH is equal to our pKa plus the log of our base over our acid concentration. Okay. One assumption this makes is that our initial is about equal to our final for both our weak acid and our weak base. This is due to Le Chatelier's principle. This is also what we did when we used the ice chart. We made the assumption that x is small for both our numerator and our denominator. And so that is just another way we could say that is state that assumption. Okay. If we were to go through deriving this, this actually comes directly from our equilibrium expression. So if we have our general equilibrium expression here, we were to switch H3O plus and Ka, rearrange the equation like that, then take the log of both sides. This would be what that looks like. And then if we were to do a little rearranging and split our logs up, we would get the negative log of H3O plus, aka pH, is equal to the negative log of Ka, also known as pKa, plus the log of our base over our acid. Okay, so hopefully that makes some amount of sense, that it is actually derived from our equilibrium expression, but all you should need to know is that anytime we have a buffer, use the Henderson-Hasselbalch equation. Okay. This also leads us to some of the terms related to buffers. So buffering capacity. This is defined by the effectiveness of a buffer by how much strong acid or strong base can be added without essentially running out of usable parts of the buffer. And in our most efficient buffer, the concentration of our weak acid and weak base are going to be equal. Okay. If our ratio of weak acid to weak base is greater than 10 to 1 or 1 to 10, then those values, then we would say that our buffer range is exceeded. And so the reason that is, if we take the log of 10 or the log of 1 over 10, then that is equal to plus or minus 1 in our Henderson-Hasselbalch equation. And so what that means is that if we want to make a buffer, our buffering capacity needs to be within a range where any pH we want to be at is within 1 pH unit of our pKa. So for example, if our pKa is 4.84, then we would not want to exceed 5.84 or 3.84 as far as our buffering capacity. Okay. Hopefully this also makes sense that the larger our concentration of our weak acid and our weak base, the better the buffer is, or at least the more neutralizing power that it has. Okay, so hopefully that makes some amount of sense just with basic stoichiometry considerations. Okay, that's it for this pre-lecture. Hopefully that was helpful. If you have questions, please do feel free to let me know. Otherwise, I will see you in class. Oh, and one more thing before we go. This may come in handy for the quiz. So just want to let you know a little something in my life. Over spring break, I'll actually write it here, I went to Sequoia National Park, and it was a great little trip. So I hope that information might come in handy for you at some point in the very near future. But just to restate that, over spring break, I did a little trip to Sequoia National Park. Anyway, hope you have a good rest of your day, and I will see you soon.